Welcome back to the exam preparation video series for DP-100, Designing and Implementing a Data Science Solution on Azure. I'm Aravind Sridharan, a Microsoft Technical Trainer. This is the second episode out of the total 4 episodes in this series. In this episode, we'll focus on exploring data and running experiments. We'll cover how to use automated machine learning to explore optimal models, use notebooks for custom model training, and automate hyperparameter tuning. Here's a list of the possible skills for your exam. They may or may not appear. This list isn't exhaustive, and while we won't be covering every skill in this video, be sure to be able to perform these skills before taking the exam. It is important to be aware of AutoML and how to use the tool. AutoML is useful because it automates the process of training and tuning models to identify the best performing model for your data. You should also know how to choose the right task type based on the problem you're trying to solve. Recall the steps to set up AutoML to train computer vision models. Select your task type, for example, classification. Configure the training and validation data. Configure the compute to run the job. Configure featurization, and then your model algorithms, and submit your AutoML job. Check the outputs and evaluation metrics, and finally, register and deploy your model. Let's recap the different types of services that are available in Azure for training machine learning models, and understand that AML integrates with a large set of open source libraries with numerous algorithms to choose from. Azure services for training machine learning models include Azure Machine Learning, which is ideal for model training with a code-first approach. Automated Machine Learning, or AutoML for short, simplifies the process by automating the selection of algorithms and hyperparameters. Azure Databricks provides a collaborative environment for big data analytics and machine learning. Fabric supports data science workflows as well. Algorithms in open source libraries available in Azure Machine Learning include regression algorithms like linear regression, decision forest regression, neural network regression, classification algorithms, which include logistical regression, decision forests, support vector machine, and clustering algorithms, including k-means clustering, principal component analysis, and even anomaly detection algorithms, which include one-class SVM and isolation forest. Know why you would use a terminal. It allows you to easily install packages and do so in a programmatic manner. Using different kernels can also be advantageous since some kernels have certain packages pre-installed. Understand what data stores are and what they are a reference to. They reference existing Azure storage accounts. The URI is a reference to a path on Azure storage account. This now becomes an asset that you can reuse. Use the data store URIs to directly start reading data from a storage location, such as CSV files, etc. Once the data is loaded, you're able to read and start exploring your data. It is vital to be aware of how powerful distributed computing frameworks are in machine learning. They can be great for large machine learning jobs, given Spark's distributed approach to data processing. Apache Spark Framework provides that service within Azure Machine Learning through managed serverless, on-demand, and Apache Spark clusters. As a data scientist, if you intend to clean and manipulate your data at scale, PySpark would be the language of choice, since it's like Python, and it can interface with Spark-based systems. Recall the steps to configure a Spark session. Select Configure Session, select the Apache Spark version from the drop-down menu and the instance type, input a Spark session timeout, then choose the executor and driver size, add the necessary configuration settings, and finally start applying and transforming your data. You must understand the feature retrieval specification capability. A data scientist does not need to understand how to create a feature store. However, it is recommended to know how to retrieve features. A feature retrieval specification is an artifact that defines a list of features to use in a model input. The features in a feature retrieval specification must exist in a feature set registered in a feature store. It can exist in multiple feature sets and multiple feature stores. Understand ML flow well and what it's used for. It is used to log and track your training, job metrics, and model artifacts. Be aware of how to configure ML flow. The steps to configure ML flow are, if you're running a job on a local machine or on a different platform, configure ML flow to point to the desired workspace and set it to the workspace training URL. This ensures all the tracking data is sent to the right location. Then create an experiment. To start training a model using ML flow in a notebook, you need to create an experiment. Run the appropriate command in a notebook cell to do this. If you don't create a specific experiment, MLflow will default to using the experiment name default. Creating a specific experiment helps in organizing and managing your experiments more effectively. Once the experiment is started, you can log metrics such as accuracy, loss, and other relevant metrics using MLflow. Following these steps ensures that your model training process is well organized and all the necessary data and metrics are properly tracked. Understand that for each model, automated ML generates metrics and charts. You may be aware of some of these metrics here, such as classification metrics. Automated ML calculates performance metrics for each classification model generated by your experiment. These metrics are based on the scikit-learn implementation, like confusion matrix, which provides a visual for machine learning models in making systematic errors in its predictions and classification models. Be aware of other metrics like the PR curve, lift curve, cumulative gains curve, but you're not going to be tested on your data science knowledge on the exam, so just be aware of that. There are regression forecasting metrics. Automated ML calculates the same performance metrics for each model generated, regardless if it's a regression or forecasting experiment. These metrics also undergo normalization to enable comparison between models trained on data with different data ranges. Metrics like residuals histogram, this is a residuals chart that looks at the prediction errors, the residuals, generated for regression and forecasting experiments. The predictive versus true chart for regression and forecasting experiments. The predictive versus true chart plots the relationships between the target feature, the true and actual values, and the model's predictions. Be aware of the different hyperparameter sampling methods in Azure Machine Learning. There's random sampling, which randomly selects a combination of hyperparameters from the specified ranges. Grid sampling, which explores a defined subset of hyperparameter space in a systematic manner. All possible combinations of the hyperparameters within the range can be tested, providing a comprehensive valuation. Then there's Bayesian sampling, which utilizes Bayesian optimization techniques to efficiently navigate the hyperparameter space. And then there's Sobol sampling, which generates samples using Sobol sequences, which are type of low discrepancy sequences. These models and methods are essential for efficiently exploring hyperparameter space, allowing for improved model performance with fewer trials. You need to understand how to define the search space. Hyperparameters can be classified into two types, discrete and continuous. Their values are described using parameter expressions. Discrete hyperparameters are specified as a choice among discrete values. The parameters include learning rate, comma-separated values, and batch size, which are range objects. In contrast, continuous hyperparameters are specified as a distribution over a continuous range of values. Understanding these types of hyperparameters and how to express them allow for more effective tuning and optimization of machine learning models. Be aware of how to specify the primary metric in a sweep job. It is the key performance indicator used to evaluate the model's performance. Its name must precisely match the name of the metric logged by the training script. This ensures consistency and accuracy in tracking model performance. The goal specifies whether the primary metric should be maximized or minimized during the evaluation of the model. It can be set to either maximize for metrics like accuracy or minimize for metrics like loss, depending on the desired outcome. This would be a great exercise to practice in a lab. Azure Machine Learning supports several early termination policies to optimize resource usage and improve efficiency. You should know how to use the different early termination policies. There's the bandit policy, which terminates runs that are unlikely to outperform the best run so far, rather focusing resources on the most promising candidates. The median stopping policy stops runs that are performing worse than the median performance of all runs, ensuring that only the top performing runs are allowed to continue. The truncation selection policy terminates a certain percentage of runs based on their performance, allowing the top performing runs to proceed. The no termination policy does not terminate any runs, allowing all runs to complete regardless of their performance. Some configuration parameters to be aware of is that you should know how you can configure the following parameters to control when a policy is applied. Evaluation interval specifies the interval in seconds at which the performance of the runs is evaluated to decide if a run should be terminated or not. Delay evaluation specifies the delay in seconds before the first evaluation of the run's performance is checked. To recap, in this episode we discussed how to use automated machine learning to explore optimal models, use notebooks for custom model training, automate hyperparameter tuning. Remember, this group accounts for 35 to 40% of the exam, so keep that in mind when preparing for the exam. Thank you for watching episode 2 on exploring data and running experiments. Be sure to join us for episode 3 where we cover training and deploying models.